Hey everyone, welcome to the Unit 2 Day 2 notes on the unit circle. Before we get started, I just want to make a quick reminder that you pause the video as you need to jot down any important notes or to make sure that you write down any questions that come up while you watch the video so that we can address them in class. All right, so let's get started. This is the unit circle. A unit circle is a circle that is graphed on a coordinate plane with its center at the origin of the coordinate plane. It's called a unit circle because the radius is exactly 1 unit long. So that means that this point right here is at the point 1, 0. We are 1 unit to the right of the origin and 0 units up. This point would be at 0, 1 because we are 1 unit above the origin, negative 1, 0, and 0, negative 1. Okay. Finding these points is going to be a little bit trickier because while the radius is exactly 1 unit away, the coordinate, meaning the horizontal distance and the vertical distance, is not 1 unit. So this point is not at 1, 1. It's some distance away that we're going to need to figure out. It's some distance horizontally and some distance vertically away that we're going to have to talk about. So we're going to figure out that in just a minute. But let's talk about the angles. We learned that to graph an angle in standard position on a coordinate plane, that means it needs to start on the positive x-axis. So an angle that doesn't move from that position is a 0-degree angle, and it's 0 radians. Additionally, if we go exactly 1 rotation around the circle, meaning our terminal side ends up on top of our initial side, that's a 360-degree angle, or 2 pi radians. A quarter of a turn would be 90 degrees, or pi over 2 radians. Halfway around the circle would be 180 degrees or pi radians. And 3/4 of the way around the circle would be 270 degrees and 3 pi over 2 radians. Okay, the important other angles on the unit circle are 30 degrees, 45 degrees, 60 degrees, and in radians pi over 6, pi over 4, and pi over 3. And then those same matching angles in all of the other quadrants. So as we keep turning, 30 degrees further from 90 would put us at 90 degrees, 135 degrees or 45 degrees away from 90 degrees, 150 degrees, 210 degrees, 225 degrees, 240 degrees, 300, 315, and 330. You'll see that these are all matching angles within each quadrant to quadrant 1. And again, we have our equivalent radians as well. Make sure that you take the time to copy these correctly. Okay, so now that we have all of our angles filled in, let's talk about how we get the coordinates. So we're going to have to go back to when we learned about special right triangles in geometry. So if you recall, we had 2 types of special right triangles. We had a 30, 60, 90 right triangle, and what we learned about them is that the ratio of the sides was always constant in a 30, 60, 90 right triangle. The short side, the one across from the 30-degree angle, was always half as big as our hypotenuse, or in other words, our hypotenuse was always twice as big as that side. And our side, our long leg, the side across from the 60-degree angle, was always the square root of 3 times bigger than our short side. So because the 30-degree angle is one that's special that we look at on our unit circle, we can apply the special 30, 60, 90 right triangle to it by creating a right triangle using the radius of the circle as a hypotenuse, and we know that the radius is 1 because all of the radii in the circle have to be the same. And what's interesting is if I create an angle in standard position, I can complete a right triangle by dropping a vertical line from the hypotenuse straight down. The reason why I want to do that is because this point right here becomes the height and the width of this right triangle, because it's the x-coordinate and the y-coordinate, or the horizontal distance away from the origin and the vertical distance away from the origin. So now I can apply my rules of special right triangles to find the height of my right triangle here, which will be the y coordinate, and the width of my right triangle, which would be my x coordinate. So if we recall that the hypotenuse was 1, this is our 30-degree angle. This is the side across from the 30-degree angle, or opposite that 30-degree angle, so this has to be 1/2. So the height of this triangle is 1/2. The width of it is square root of 3 times bigger than 1/2, or in other words, the square root of 3 over 2. We have exactly the same 30, 60, 90 right triangle in all other quadrants. So we have another one here, another one here, and we can create another one here. Meaning that these points will all have matching coordinates, but just different signs based on the quadrant that we're in. So in quadrant 2, this 30, 60, 90 right triangle still has a height of 1/2, and it still has a width of square root of 3 over 2. It's just negative because now we're in quadrant 2 where all of our x coordinates are negative. Here, with this right triangle, our height is still 1/2, but it's negative 1/2 because we're in quadrant 3 where all of the y coordinates are negative. The width is still square root of 3 over 2, but it's a negative because, again, we're in quadrant 3 where all of the x's are negative. And finally, we said we had an identical triangle here, 30, 60, 90 right triangle, and in quadrant 4, the x's are positive and the y's are negative. So it all comes from this matching 30, 60, 90 right triangle. So the second thing that's interesting is that 60 degrees also happens to be on our unit circle, and it's obviously still part of a 30, 60, 90 right triangle. In this case, the 60-degree angle is the one that we're creating with the positive x-axis in standard position. So it's the height now that's across from the 60-degree angle. So that's the square root of 3 over 2 side. The width is the one that's across from the 30-degree angle. So that's the 1/2 side now. And again, this same triangle is mimicked in all the other quadrants in the same way, but with matching signs based on what quadrant you're in. So negative x's, positive y's. Negative x's and negative y's. And then finally this one here, positive x's and negative y's. So the unit circle has a lot of information on it, but it's a lot of repeated information. Okay, so finally we have this 45-degree angle, and I did it over here just to kind of show you that it's exactly the same triangle. This is going to be a 45, 45, 90 right triangle. And in this triangle, the hypotenuse is the square root of 2 times bigger than your two legs, and your two legs are congruent because it's an isosceles right triangle. So if I drop a vertical line straight down and I continue my angle here at the origin, that makes the horizontal and the vertical my x and my y coordinate, and the hypotenuse is 1. So if the hypotenuse is 1 and it's the square root of 2 times bigger than the legs, then that means that the legs are 1 over the square root of 2 times smaller, or they're the reciprocal. So 1 over the square root of 2 we don't like because it's got a radical in the denominator, so we need to rationalize it, which we'll practice in class, and that makes it the square root of 2 over 2. And because they're the same, they're both the square root of 2 over 2. This one's negative just because we're in quadrant 2. But it's exactly the same here with positive x's and y's. In quadrant 3, it's exactly the same just with negative x's and negative y's. And in quadrant 4 with a positive x and a negative y. So here you can kind of more clearly see our right triangle with a hypotenuse of 1, and then therefore the leg and the leg would be 1 over the square root of 2, or if we rationalize it, the square root of 2 over 2. Okay, so why do we care about this? Why are we filling in the unit circle? We're going to use the unit circle now to evaluate trig functions at these common angles, from 0 to 360 in increments of 30, 45, and 60. So how do we do that? Well, if you remember our trig functions, They are sine, cosine, and tangent, and this year you're going to learn about 3 more: cosecant, secant, and cotangent. These are just the reciprocals of sine, cosine, and tangent. So we'll talk about that more in just a minute. Back in geometry, you learned that the sine of an angle in a right triangle is equal to the opposite side over the hypotenuse. Remember SOHCAHTOA? So in this triangle with the 30-degree angle, the opposite side was the vertical side and the hypotenuse was the radius. So the opposite side, or the vertical side, has a value of 1/2, and the hypotenuse is 1, and anything divided by 1 stays the same. And the hypotenuse of all of these circles is always going to be 1. So to find the sine of an angle using our unit circle, all we need to do is find the y-coordinate at that point. So on the unit circle, the sine of an angle is equal to y. Cosine, we learned, is adjacent over hypotenuse, and the adjacent side of all of these angles that are graphed on the unit circle is always going to be the horizontal distance, or the x-coordinate. Because the hypotenuse, it's also over the hypotenuse, because the hypotenuse is 1, cosine is adjacent side over hypotenuse, anything divided by 1 stays itself, so cosine of any angle on the unit circle is always going to be the x-coordinate. And tangent, we learned, is opposite over adjacent. The opposite side is the vertical side, the adjacent side we just said is the horizontal side, so it's always going to be the y-coordinate over the x-coordinate. Again, this only works for angles that can be found on the unit circle. Okay, now cosecant, we said, is the reciprocal of sine, so the reciprocal of y is how we'll find cosecant. So let's say our y is already a fraction. We don't necessarily have to put it under 1. We can just flip that fraction upside down. So this just means reciprocal. It doesn't mean you have to put the fraction under 1. You can and simplify it, but you don't have to. Secant is the reciprocal of x. So if your x-coordinate is already a fraction, all you have to do is flip that fraction upside down. And cotangent, which is the reciprocal of tangent, is x over y. Finally, the last thing to talk about is which trig ratios are positive and negative in which quadrant. So in quadrant 1, where all of the x's and the y's are positive, all of the trig ratios are positive. None of them are negative. But in quadrant 2, where all of the x's are negative, that means that this is a mistake. Sorry, I'm getting myself confused. Where all of the x's are negative, cosine will be negative, and so will tangent and cotangent because they have a negative in their ratios. And cosine is also negative. I'm sorry, cosine is negative because the x is negative, but secant is also negative because it's the reciprocal of x. Sine and cosecant are positive because they're made up of the y-coordinates, and the y-coordinates are positive in quadrant 2. In quadrant 3, everything's negative, the x's and the y's. So sine and cosine, as well as their reciprocals, are negative, but tangent and cotangent are positive because the two negatives cancel each other out in their ratios. And then finally in quadrant 4, where the x's are positive but the y's are negative, sine is negative because it's the y and its reciprocal is negative. Tangent is negative because it has a y in it, as well as its reciprocal cotangent. But because x's are positive, cosine and secant, which are only made up of the x-coordinate, are still positive. And that's the unit circle. Come to class with any questions. Thank you for sticking in and hanging in there.